In my previous video I have explained you about the point defects, right? Today I am going to cover the remaining defects. So today I will start with the line defect. Normally this line defect, it is going to arise when you are going to add or delete, or there is any misalignment of the line of atoms from its designated ordered arrangement. So this kind of line defects, it is going to created. Okay, the line defect is also, it is known as the dislocation or distortion of line of atoms. If there is any distortion in the line of atoms, so that we are considering it as a line defect. And also this line defect, we are calling it as dislocation. This defect occurs during the solidification of material or during the plastic deformation. This line defect, it is going to occur. During plastic deformation, there is a large movement of atoms due to the applied force. So hence, the dislocation of atoms will be there. So when there is a dislocation of atoms along the line, so this kind of linear defects is going to happen. I told you the linear defects also we are calling as a one-dimensional defect. Okay, so along the line, the movement of the atoms will be there. So that this kind of linear defects or the line defects, it is going to happen. So here in this diagram, see here, this is the upper region, so this is the lower region. Okay, so the dislocation, it is the region of localized lattice distortion which separates the slipped and unslipped portion of the crystal. Okay, so normally when there is a dislocation, so this dislocation, it will separates the slipped and unslipped portion of the crystal. The upper region of the crystal over the slip plane has slipped relative to the bottom portion. So the line here, the AD between the slipped and unslipped portion is the dislocation here. Okay, the magnitude and direction of the slip produced by the dislocation is the Berger vector B of the dislocation. So here the AD is the line, okay, that it will separates the slipped and unslipped portion in the dislocation. So normally the dislocation we are going to find out with the help of Berger vector. The Berger vector, it will give you the magnitude and direction of the slip. In linear defects, we have edge dislocation and we have screw dislocation. Okay, first we will see what is edge dislocation. In this type of dislocation, the Berger vector is perpendicular to the dislocation line, and the distortion, it produces an extra of plane above the slip plane. So here, normally in this edge dislocation, the Berger vector always it is perpendicular to the dislocation line, and also due to the distortion, it will produces an extra plane of atoms above the slip plane. So here, these are the extra plane of atoms. This extra plane of atoms, it is produced due to the distortion. So above the plane here, the extra plane of atoms are produced, right? So this normally will indicate with this symbol reverse T. Okay, so here very clear you can observe. So these are the extra plane of atoms. Okay, this extra plane of atoms are producing because of the distortion in the plane of atoms. So normally the slip vector, it will be in this direction. Okay, so normally in Berger vector, always it will be perpendicular to this dislocation line. An edge dislocation we can illustrate by slicing out a part through a perfect crystal structure, or spreading the crystal apart and partly filling the cut with an extra plane of atoms. Suppose here I am considering this. So how we are going to produce the edge dislocation means, so suppose if you are slicing out a part of perfect crystal structure and you are spreading the crystal apart, and the partly you are filling out with the extra plane of atoms. So like this, so we are going to get this kind of edge dislocation. Okay, in the crystal structure, the region near the dislocation, it will experiences local lattice distortion, and the atoms above the dislocations are squeezed together, and those below the dislocation are pulled apart. Okay, so the magnitude of this lattice distortion is higher near the dislocation, and it will decreases with increasing distance away from the dislocation. Suppose if the insertion of extra plane is on the upper side of the defect, is represented as positive dislocation, and also which is denoted by this. Here you see this symbol we are going to use for representing the positive edge dislocation. So when it is going to be represented with this symbol means the extra plane of atoms, suppose it is upper side of the defect, so we are going to call it as the positive dislocation, and we are going to represent with this kind of symbol. Suppose if the insertion of extra plane of atoms is lower side of the defect, then we are going to represent as the negative dislocation. The negative dislocation, so we are going to represent with reverse T. So T, normal T symbol will be there, right? So with that we are going to represent it. So reverse to this, reverse. So next one is the screw dislocation. Okay, the screw dislocation, it is one other type of dislocation. In this, the Berger vector is parallel to the dislocation line. See here, this is the Berger vector. Okay, so the Berger vector, it is always parallel to this line, dislocation line. So normal dislocation, it will be in this line, and the Berger vector also, so it is in this direction. So always the Berger vector, it is parallel to the dislocation line, but in the edge dislocation, the Berger vector always it is perpendicular to the dislocation line, right? So that is the difference here. And the trace of the atomic planes around the screw dislocation, it will make a spiral or helical path like a screw. So that is why it is called the screw dislocation. The atomic positions along a screw dislocation, it is represented in these diagrams. So normally when there is a screw dislocation, the atomic positions along the screw dislocation, it will be like this. So here you can observe very easily the dislocations how it will be. So AD in this direction, the dislocation will be there. Okay, so normally in screw dislocation also, so there is a positive and negative dislocations will be there. Okay, suppose if the upper portion of the crystal structure is shifted towards the right, okay, with respect to the lower portion, then the defect is represented with clockwise direction symbol. Okay, suppose if the upper portion of the crystal structure is shifted towards the left with respect to the lower portion, then the defect is represented with the anti-clockwise direction. Okay, so that defect, it can be imagined that produced by cutting of the crystal structure partly by a knife, and subsequently a shear of a part of crystal along the plane parallel to the cut. So this is the Berger vector. The Berger vector we are going to use for the line defect. Okay, the Mr. Berger, the crystallographer, devised a method to show the line defect. The Berger vector, it will indicate the magnitude and direction of the dislocation or the shift of the lattice line on the slip plane. The method is based on the loop or a circle method. This Berger vector is formed by drawing a vector lattice translations, that is lines around the boundary of equal length on the parallel sides. For a perfect lattice structure, the Berger vector will form a closed loop or the closed circuit. In case of defect, the Berger vector will fail to close. Okay, so here you see, suppose if it is a perfect crystal structure, so this circuit or the loop, it will be closed perfectly. So here it is starting, right? So equally we are moving. Okay, the equal length of the parallel sides will be there, so we are moving one by one step. Finally where it is, here it is finishing, right? But it is not closed. but when there is a defect, it normally it will be like this. So there is no closed loop will be there. Okay, suppose if it is a perfect crystal structure, this loop or the circuit, it will be closed perfectly. Normally, when there is a line defects or the dislocations in the material, so how it is going to affect? Normally, the line defects affects the various properties of the materials. It will affect the mechanical properties, like it will increases in hardness and the tensile strength, and also it will changes the transformation properties also. Because of adding of atoms in the structure, it will increases the recrystallization temperature and other phase transformation characteristics. And even the electrical resistance also, it is going to be increased with distortion in the material, and the corrosion resistance also, it will be decreases with distortion of lattice structure. So this is the dislocation, movement and deformation, how we are going to calculate. Normally, the theoretical shear stress to produce the plastic deformation in the metals. So we are going to represent with this formula, tau is equal to G by 2 phi, right? So here the G is the shear modulus for the materials. In the larger range, it will be 20 to 150 gigapascal. The yield strength, it will be 3 to 30 gigapascal. Okay, so normally if you calculate the value, the yield, it will be in between 0.5 to 10 megapascal. This discrepancy can be explained by the presence of the dislocation in the lattice. The dislocations, it will assist in plastic deformation, since it is easier to move the atoms at the dislocation core. The movement of the dislocations, it will produces a slip step of one Berger vector or the one interatomic distance. So here they are showing how the movement it will be there when there is a slip, how the atoms or the plane of atoms, how it is going to shifted or how it is will be moved from one side to another side. The dislocations, it will move in steps. So if you see this diagram, the this atoms, how it is going to move from P to Q, we'll see. Okay, the edge dislocation at point P, it moves to Q in steps as represented by red. Okay, this is extra plane of atoms and the blue atoms. This movement is analogous to movement of the caterpillar. The edge dislocations can move only on the slip plane, while the screw dislocation do not have any fixed glide plane. Since the plastic deformation, it will takes place by movement of dislocations. Any hindrance to the motion, it will increases the strength of the material or the metals. So here we can observe the dislocations, how it will be when you see the dislocations under the transmission electron microscope. So the surface defects, we can call it as the 2D defects. We can call it as the 2D defects because here there is a different boundaries will be there, the gain boundaries. Okay, the surface defects are associated with the boundaries that are separate regions of the materials, and it will have the different crystal structure or the different crystallographic orientations. The defect, it may be due to the change in the orientation of the atomic planes or the change in the stocking sequence of atomic planes. So that is why it is a called as the two-dimensional defect. This defect, it may be caused during the solidification or the mechanical or the thermal treatment of the material. In surface defects, again we have different types: the grain boundary defect, fin boundary defect, and the low angle boundary defect, and the high angle boundary defect, and stocking defects will be there. So normally these grain boundaries act as an obstacle to the destruction motion. So that the presence of more grain boundaries, it will increases the strength, because the grain boundaries, it will act as a huddle to movement of the atoms in the lattice, so that if there is no movement of the atoms or there is no slip, actually the strength of the material, it is going to be increased. So here you see the grains, different grain, different orientations of the atoms in the lattice. So here this orientation, it is different, and here it is different, and here it is. So these are the three different grains. So here this is the region, so that it will separate the different grains, that is the grain boundary. So the last one is the volume defect, or the we can call it as the three-dimensional defect. The three-dimensional defect, it will produces the porosity, inclusions, and cracks. These defects, it will form during the manufacturing process for various reasons, and also it will harmful to the material. So here these are the some of the examples where we are going to get this kind of bulk defects or the three-dimensional defects. So here when we are going to do the welding, so we are going to get this kind of defect, and also during the casting and shrinkage, uh, we are going to get these three-dimensional defects. Casting blowholes, the porosity, the gas entrapping during the melting and pouring. So we are going to get this kind of bulk defects. Suppose if there is improper welding parameters or the practices we are using, so that we are going to get this kind of defects. Normally the shrinkage cavity you are going to get due to the improper rising. Non-metallic inclusions we are going to get because of slag and acid particles or sand particle or sand entrapment. Even we are going to get the cracks because of uneven heating or cooling, or there is any thermal mismatch, or the constrained expansion or contraction. This all leads to the stress, so that we are going to get this kind of the three-dimensional defects. Thank you.